My name is Vamadevan Namboodiri and I work for .com. I do my part-time PhD at Rutgers University as past week. I'm going to give a presentation about low complexity equalization applied to OFDM systems. Well, what is so great about OFDM? See, we have many different modulation techniques: the single carrier, QAM, and multi-carrier OFDM. Generally, most of the standards coming nowadays are OFDM based, and that is primarily because of the high, the simplicity in the receiver design. Yet, you can support pretty high data rates. Now, one of the weak points for OFDM is when it comes to when the receiver or transmitter is moving, that will induce a Doppler frequencies, and that will cause the orthogonality loss of intercarriers, and that will cause intercarrier interference. And you need an equalizer to cancel off the intercarrier interference. And when you talk about equalizers, the main beauty of OFDM is that you do not need a very complex equalizer. Whereas by virtue of the fact that you have ICI, you are forced to have an equalizer. And our idea here is to come out with an optimal equalizer solution, which in terms of area and cost. So what is available today? We have three different kinds of, generally speaking, we have three different kinds of equalizers for OFDM. One is the traditional one, which is the decoder and the symbol estimators detector, they call it, and they are separate. And that is the traditional one that we have been. That's the traditional one, the classical one. And there are tons of such architecture available in the literature, and some of them are MMSE based, some of them are polynomial cancellation. What I mean by that is, if you have intercarrier interference, and generally if you have Doppler frequencies, then generally it follows J spectrum, so you fit in a polynomial and find out the coefficients for that and cancel off your interference. That's the first kind of equalizers. The second one is the successive interference cancellation based. What you do there is you make a preliminary estimate of your OFDM symbol, and then use that and convert it back into the time domain, and use that information together with the time domain channel information and compute the interference and remove it from the received data, and then convert it back again to the frequency domain and do the slicing and keep iterating between time and frequency domain. That's the second type. And the third type is the turbo equalization based. There, what happens is you iterate between the detector and decoder, and basically you leverage on the coding gain of the decoder to get better symbol estimates. And we are going to see a bit in detail on the third one. And among all the three, the best one is the turbo equalizer based. The caveat for this is that they are pretty intensive in terms of area, silicon area, and in terms of computation complexity. So, as I said, so turbo equalizers was originally proposed by Duyat. It has the original, the one which was invented in late 90s, had exponential complexity, which is not easily implementable at all, and which was then A simplified turbo estimation, turbo equalization was proposed by Tutzler and team. It had a cubic complexity, cubic mainly because of a matrix inversion involved. And then when the idea was further taken, was further enhanced for OFDM-based systems by making, and the computation complexity was cut down a lot by making use of the sparseness of the system matrix. We will see that shortly how. That has a complexity something of the order of OND cube, and D being the small submatrix X. Still slightly higher than N, linear complexity, but much less than the cubic complexity that we have seen just above. Now, the question now is, can you bring down the complexity further? Yes, and that is our scheme. Before we get into our scheme, let's just put things in perspective. This is the kind of system model that we are talking about. You have a convolutional encoder. You have information bits coming in, and it is getting convolutionally encoded, and it is time interleaved, and then it is mapped to QPSK, BPSK, 16 quant, or higher order modulations. Whatever is coming out from there is frequency interleaved, and then the standard OFDM processing, which is inverse FFT and cyclic prefix addition, and the standard OFDM processing. That is what is transmitted across the channel. And the channel in our case is, we assume that it's a mobile channel. That's why linear time varying channel. And at the receiving end, the noise is getting added, and you do the, upon the reception, you have the noisy observations, RIs, which are getting into the receiver, and the receiver processing, the standard OFDM receiver processing is being done there, and you get YKs, which are the symbols that are getting into our equalizer, into a standard turbo equalizer. Now, we'll see the signal flow at the equalizer in a slightly greater detail. Whatever is coming out of the equalizer's job is to compute the symbol estimates, and it does that. Whatever the symbol estimates, x hat case, or frequency de-interleaved, just the opposite of frequency interleaving, is done, and the frequency de-interleaved symbol estimates are converted to soft information, log likelihood ratios in the soft demapper, and whatever that LLRs, time de-interleaved LLRs are fed to a BCJR based decoder, and whatever is coming out of the BCJR decoder will be again log likelihood ratios, soft information otherwise, and that is passed on to a soft mapper, which will convert into a soft mean and variance, which is another input to your MMSC turbo equalizer. And this is the iterative loop. That is how it iterates between the equalizer and the decoder. After a few iterations, once you get sufficient convergence, the LLRs coming out of the BCJR decoder are hard sliced, and you get the information which they had had. So this is the general flow of information between the transmitter and receiver to the channel. Now, in our presentation, we assume a baseband transmission. There is no carrier frequency. We are not talking about carrier because it is relevant. It's not all that important for when we talk about the equalizer. We are assuming baseband transmission, and we assume for now that channel is not the equalizer. You need a channel estimator block to find out the channel values, but that is covered in that's another topic altogether. So the system model is y is equal to hx plus w, w being the noise, x being the input information vector, and H is channel matrix. A little bit of math here. This is the standard linear estimate equations. The simple estimate is given by the first equation, and by x hat k is given by this equation. This is the standard MMOC formula. If we substitute for mean value of xk and this, and covariance of the cross covariance of xk and y and this from the system model, remember y is hx plus w, you get this formula where mu xk is the mean of the current symbol value, and vxk is the variance of the present symbol that we are trying to estimate, and ikh Hermitian is the kth row of the system matrix that we have seen a moment ago, and sigma y is given right here. Note here that in order to compute sigma y, you have matrix. This is a diagonal matrix generally, and you have a matrix multiplication and a matrix inversion. So that is the most computationally expensive one. And mu y is hxy is the mean value of the received symbols. So remember this formula. This is in the turbo equalization. Our idea is to implement equation 1, and we are going to see how. If you do not have turbo equalization, if you have ordinary MMSE estimation, you assume that mu k is 0. This is 0, and this is 0, and this is 1, and that is the usual regular MMSE estimation. Okay. So we are just seeing the same block that we saw a moment ago, with a little bit more details. You see as we saw the channel equalization, this channel symbol estimator block. This is a new block we have designed. We are going to see details of these red blocks in the subsequent slides. So basically, we have 5 different blocks in this configuration. One is the symbol estimator and the mapper and demapper. We are going to see them in detail. And you have the frequency interleaver and de-interleaver, time interleaver and de-interleaver, and the DCJR, the decoder, block based on DCJR algorithm. So 3 plus 2 plus 1, 6 blocks. Now, what is the extra? Okay, we would need this information in the subsequent slide. We would need this information. In the previous slide, we saw our idea is to implement equation 1. How to come up with an algorithm to implement equation 1, out of which you need variance and mean values. Here. And the way we compute, we need to know what is when in terms of. So going through this slide again, so you get the symbol estimates using turbo equalization, and you get the log likelihood ratios, and from the BCJR you get extrinsic information. We are going to see what that is. And that extrinsic information is time interleaved, and fed to the soft mapper to get the mean values and variance values. So what is extrinsic information? That's a question we are trying to answer here. Extrinsic information is okay. The way we can look at extrinsic information is like, whether it is a decoder or a channel equalizer, you have. You can consider them to be like like LLR, log likelihood ratio transformers. You feed in a log likelihood ratio at the input, and you get another, generally a slightly higher log likelihood ratio at the output, generally speaking. And so it's a transformer, and the difference between them, the input and the output and the input, is the extrinsic information that was built up by virtue of the structure within the BCJR, or for that matter the channel equalizer. So that is that is the extrinsic information. And in all our computations, LLR computations and soft mapper, we use only extrinsic information. The reason being, it's been found that if we use extrinsic information, the convergence properties will be generally better. Now, as we saw earlier, the idea is to bring down the size of the matrix to be inverted as small as possible, to see possibly whether we can do it by an element inversion. So before we do that, let's talk about the structure of the H matrix that we are trying to deal with. It'll be just a diagonal matrix if you have only a static channel. Whereas if you have ICIs, you will have a banded structure with the diagonal elements and one or two sub and super diagonals with the non-zero elements, and the rest of them will be insignificant elements. So the idea is to ignore these bands and just make use of these. And how we are going to, and generally, depending on higher the Doppler, wider this would be, and in the limiting case, when there is no Doppler, it will be just diagonal. What we can see are, these are three crucial observations that are which we have heavily leveraged on to come out with our scheme. The relative magnitude of the off main diagonal elements in the earlier slide are smaller than the main diagonal elements, even at high Doppler frequencies. That's one big finding. The other one is the relevant magnitude of each sub-diagonal element of the H matrix decreases significantly as it moves away from the main diagonal. As you go away from the main diagonal, as you go like this, the magnitude comes down drastically. And as we saw earlier, as we discussed, these elements here will be very close to zero, that you can conveniently ignore them. Another one is, as the LLR, once you iterate through after a few iterations, the log likelihood ratios gets more and more accurate, and once it's more and more accurate, the conditional variance tends to zero, and conditional mean of each symbol value tends to the original symbol value. That is a very key observation. Yeah, we saw these details in an earlier slide, and we discussed this. So in the earlier slide, we had three blocks that we wanted to discuss, out of which the soft mapper, we have already seen this. The soft mapper computes the mean symbol estimate from the LLRs, and we have derived the new equations for this that will fit into our scheme. Our main contribution is the symbol estimator, a new way of finding the symbol estimation. And how we do that. So we have seen that the key observation is that we can get and this is by far the most important slide. We get the mean values as we iterate, as we progress in iterations, we get more and more accurate mean values. And so what we do is, using the mean values, you compute the interference. You have the channel matrix available, and you take the banded matrix, and for each of the symbol values, we'll see the mathematics soon. But for each of those, what we do is we compute the interference for using those symbol mean values. We compute the interference and negate of the interference from the observation, so that the resultant matrix will be like that of static, so that you will have only diagonal elements. So the interference from the adjacent bins are computed, and it is remote. And so the residual I say from the error is small. Yeah, that will be diagonal. Once you do that, once you get the modified observations, which are ICI remote, then you can use the plain simple MMSE equation with no matrix inversion. Remember, this is an element. This is just dividing the new observation with the element with another element and get the new symbol estimate. So that's the idea. We will see the mathematics. So, and the soft demapper, which computes the soft information from the symbol estimate, is also has to be modified accordingly. And the other 4 operations are standard, which we do for the turbo equalization. Okay, here is the mathematics. So you have, this is just only a portion of the observation vector. We are talking about yk. Yk is this times this plus this times this plus this times this plus the noise. Plus another term, another noise-like term that that came from ignoring these elements. So you had all these elements. So we quantify that interference in these, which are generally pretty insignificant, and then they. And now this is xk, whereas xk is converted to mean value plus a delta difference, and xk and mu xk plus 1 like this. So what we do is we compute this times this and negate off from this times this and this times this and negate off from the yk here, and so that is the new observation y prime k, and n prime because of the delta terms, because of the additional contribution from the delta terms and these. So that's how we get this new equation, and from there it is straightforward. We get the estimation. Now, once we do this, okay, now that is about the symbol estimate. Now we are going to see how the soft demapper works. The idea here is, this is the standard idea in the turbo equalization, is to estimate the symbol errors. I mean, it is assumed that the estimation error is assumed to be Gaussian distributed with zero mean, and the variance of that is variance of the estimation error is this, and the log likelihood ratio is defined to be the ratio of the Gaussians taking the log of the ratio of the Gaussians, conditional Gaussians, with input being of the conditional log of the conditional Gaussians with condition being x equals 0 and x equals 1. This is standard definition. And once we work it through, we will get these equations for QPSK. And so that is about the demapper. And for the mapper, it's the other way around, and you get this equation. Now we are going to see the results of our scheme, and we are going to compare 5 different schemes, and let me give you a preview about the different schemes that we're using. MMSE ON is the one which where we ignore all the when you have ICI, you still ignore all the sub and super diagonals and just use only the main diagonal and this plain and simple scheme. That is MMSE ON. MMSE OND cube is taking that small the portion of that matrix in slide in an earlier slide. We are running short of time, right?
I think you're very close to the half hour mark.
Oh, is that? Okay, then you can check. Never mind. Okay, let's finish this. Okay, here the shaded portion is the HK is when you use HK for estimation, that is that MMSE OND cube scheme. Now proposed scheme is, we have seen that, and TE MMSE OND cube is the turbo version of the MMSE OND cube scheme that we discussed, and TE MMSE ON cube is the, that is in fact a mistake. It's only MMSE ON cube. Slide 14. Is taking the inversion of the full system matrix. Okay, now about the 5 more minutes, to half an hour. Okay. Okay, now the computation complexity. Here, as you can see, here is this gives the computation complexity of the MMSE plain MMSE scheme and the TSIC scheme that we have discussed now. As you see, even with the 6 iterations, you will not have as much computation as that for MMSE when D is 3, when you have moderate Doppler. At high Dopplers, the computation complexity is much less. Now, we are talking about what we are going to see soon is the simulation results with for a scheme where you have it's a 2K FFT scheme with all this setup for a QPSK modulation. And we are using rate half convolution encoder, and CP length is n over 4, and we have the simulation results for different Doppler frequencies. The normalized Doppler frequencies being 0.1, 0.2, and 0.8. Now here is the first result. When your Doppler is moderate, then all of these schemes have generally the same performance. Whereas if you look at the end, you can see that MMSE ON is the worst, and next to that is MMSE the MMSE OND cube, and next to that is our scheme, and next to that is a scheme that is turbo MMSE OND cube, and the last one is the most computationally expensive. And we will come back to TE SIC MMSE ERA in a bit. And the results are progressively clear as we go higher in Doppler. Now here is the pitfall of our scheme. When you have when your symbol sizes are pretty high, you will be, and when there is Doppler, you will see a lot of bins getting erased in a group when you have a strong fate. So because of that, a lot of channels are getting erased, and when you compute the ICA for removal, that computation will be very insignificant and often inaccurate. And because of that, you will have to, in such cases, you have to detect those cases, and in such cases, you have to use MMSE, the plain MMSE estimation, not turbo, and remove the interference. We have seen that it happens around 5% of the time when your Doppler is around 0.2. And those are the results. That is the MMSE ratio scheme that we have seen a moment ago. And this is a generic scheme. You can go for higher order modulations and convolution and different convolution codes or LDPC turbo codes. So what we have seen here is a low complexity iterative symbol estimation scheme that leverages on the feedback symbol mean values. And this is a practical scheme under power constraint scenarios because we can we can control the number of iterations at the cost of performance. So how much did we take?
I think you're about 31 minutes.
31 minutes, huh?
You're a little bit.
Yeah, should be 20 minutes at the most. All right. Any questions?